Imagine a person working the door at a crowded movie theater, taking and ripping hundreds of identical ticket stubs every single day. The human mind processes thousands of routine sensory inputs in much the same way. By biological necessity, the brain is optimized to discard almost all of them immediately. Working memory has a severely limited duration. Unless data is actively held there through rehearsal, it vanishes quickly. Passive, unremarkable information flows through this system with zero resistance, like water running unimpeded through a completely smooth pipe. The routine only breaks when a heavily textured anomaly interrupts the flow. The brain's retention mechanism requires friction. It triggers specifically for data that is unusual, highly significant, or cognitively challenging to process. This creates a distinct hazard for any learning environment. If a user encounters material they believe they already understand, they stop paying attention entirely. Without a localized reason to stop and actively process the incoming data, that familiar-looking information leaves absolutely no mark on long-term memory. If the delivery of content is perfectly smooth and familiar, human biology guarantees it will be forgotten. This biological reality creates a severe problem for modern instructional designers. The learning and development industry largely optimizes for frictionless user experiences, aiming for perfectly clear, uninterrupted content delivery. Think of the standard e-learning module, where a user effortlessly clicks next through highly polished slides. It's the purest expression of this passive design philosophy. This passive architecture channels data smoothly past the learner. It demands no active cognitive processing or reconciliation of facts. Making a learning system easy to consume is the exact opposite of making it easy to retain. To engineer actual long-term knowledge retention, system architects must abandon the pursuit of frictionless flow and intentionally design for cognitive friction. A 2008 study by Derek Muller analyzed how students learn physics concepts from video, testing highly polished clarity directly against structured confusion. This chart graphs the study's metrics. The vertical axis tracks subjective satisfaction versus objective test performance. The first cohort watched perfectly clear, highly polished physics explanations. These students gave the videos the highest possible ratings for clarity, reporting the material was extremely easy to understand. They experienced the illusion of understanding. The polished presentation allowed them to recognize concepts instantly, which they mistook for the ability to recall those concepts later. Their actual post-test comprehension scores were abysmal. The smooth delivery passed right through their working memory. The second cohort received a different treatment. They watched videos featuring dialogues that openly discussed and highlighted common misconceptions about those exact same physics principles. This second group rated their videos poorly on clarity. They reported feeling highly confused and found the material difficult to follow. Yet in objective testing, the second cohort vastly outperformed the students who watched the clear videos. By watching the misconceptions play out, the students' own false assumptions were forcefully confronted. They had to actively reconcile the contradictions to make sense of the lesson. The act of interacting with and resolving that cognitive messiness is the exact mechanism that embeds data into long-term memory. User confusion is not inherently a failure of instructional design. When engineered correctly, it is the primary metric of active engagement. Before a system can successfully deliver new facts, it must force learners to explicitly realize what they do not know. This requires metacognition, the capability of thinking about one's own thinking and tracking one's own understanding. Medical schools developed a methodology called problem-based learning to build this metacognitive architecture. Traditionally, motivated medical students could memorize vast amounts of clinical data, but structurally failed to apply it to living patients until this methodology was introduced. This whiteboard tracks cognitive gaps in problem-based learning. Given a case, students use the facts and ideas columns to inventory prior knowledge and hypotheses. The crucial function occurs in the third column, learning issues, isolating specific areas lacking sufficient data to make a diagnosis. By explicitly listing their blind spots, learners actively construct empty cognitive shelves in their own minds. They are no longer passively receiving a lecture. They are primed to actively hunt for the precise intrinsic data required to fill those specific shelves. Forcing a user to identify the boundary of their own ignorance is the architectural prerequisite for retaining new knowledge. To specify exactly what kind of friction designers should build into these systems, educational psychologist John Sweller developed cognitive load theory. This diagram represents Sweller's model. Cognitive capacity is strictly finite, divided between three distinct loads. The first is intrinsic load, the raw informational data that must be learned, like biological facts in a dinosaur course. The second is extraneous load. This is useless friction, like a glitchy interface, that drains mental energy. Extraneous load is the true enemy of the user experience designer. It must be eliminated entirely. The third is germane load. This is the desirable difficulty, the interactive friction, like a diagnostic task or a design puzzle that requires effort to complete. Germane load is the specific cognitive mechanism of chewing on the intrinsic material so it can be digested and stored. Superior learning design does not remove all friction. It systematically shifts wasted energy from extraneous load directly into highly productive germane load. This diagram serves as the ultimate control panel for any learning systems architect. Your first mandate is to annihilate all useless, non-educational friction from the interface. Your second mandate is to intentionally ramp up desirable difficulty, forcing the user to wrestle with the intrinsic material. Instructional design operates as the ruthless management of cognitive load. Never hand out passive, heavily polished conclusions. Build the environment, provide the raw data, and force the learner to construct the map themselves. Human learning is an inherently messy biological process. The most effective educational systems do not pave over that mess, they harness it.